Okay, so let's look at like when can you not use law of sines, right? Law of cosines. And there are two situations where you would be given half of the triangle's pieces. Remember, there are 6 total: side, 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 angle, angle, angle. So if you're given 3 of the 6, you can sometimes solve for the missing pieces. And so far, we've got the tool of law of sines. Now, there's another tool called law of cosines. And law of cosines works if you have a situation where you know all 3 sides, or if you know 2 sides and the included angle. So these 2 situations, law of sines does not work. You can't set up a ratio. There are too many unknowns. Like, for example, if you, again, just seeing, like, why not? Like, if, let's say, you know, this is 6 and this is 8 and this is 9, and call this alpha, call this beta, call this gamma. So notice you're given the 3 side lengths. If you try to set up a ratio, let's say sine of alpha over 6 is equal to sine of beta over 9, there's no way to isolate beta without knowing alpha, and vice versa. And you could just complete the ratio, sine of gamma over 8. So if you are given 3 side lengths, like side length, side length, side length, side length, it forms just one triangle, because side, side, side is a concrete way to show you have a triangle that's congruent to another triangle if you can match the sides. So there's no ambiguity, but you can't use law of sines. Okay. In the same fashion, if you were given, if you were given 2 sides and an angle that's included. So if I were given something like this, like, okay, suppose I know that this is 8, and I'm just making this up, and this is 12, and this is 72 degrees. So let's say this is length C. I'll call this angle alpha, call this angle beta. Again, try to set up law of sines. It doesn't work. Sine, sorry, I'm getting crazy here. Sine of 72 degrees over C is equal to sine of, pick whichever one, alpha over 8. Again, no way to solve. Or sine of beta over 12. Anytime you pick 2 of these 3 ratios, you have 2 unknowns. Okay, so introduce law of cosines. So here's what law of cosines says. And probably won't prove it in this video, but it's not super hard to prove. So, when we come back, hopefully I'll get a chance to prove that to you, or you can just look it up online, or maybe I'll link a good proof to it too, a video that's already been done. But if you have a triangle, pen, there it is. Okay, and again, I'm just going to arbitrarily just draw a triangle. Call this A, call this B, call this C. So this is alpha, this is beta, and this is gamma. That let's say you're looking, let's say you're given this side length. Oops, my bad. Let's say you're given this side length, and this angle. So you're sitting in a side angle side case. Okay, so here's how law of cosines could be used. So it says cosine, it'll be cosine of gamma, which is this angle that you're given, is equal to a squared plus b squared. Oh, sorry, I totally got that wrong. I'm solving it for another one. So let me try this one more time. Eraser, there it is. C squared equals, my bad. Go to pen color. There it is. C squared is equal to a squared plus b squared minus 2ab cosine of gamma. And what I want to emphasize is that the side that you don't know, so this side here, we don't know that side, is always opposite the angle that you do. Whether they're called C and gamma, whether they're called A and alpha, or whether they're called B and beta. There's no reason why I couldn't have said, why not call it B squared, pen, then erase this here, Still getting used to this new stylus. I apologize. So then I could say, there's no reason why I can't say b squared equals the other two side lengths, a squared plus c squared minus 2ac cosine of, well, what's the angle opposite b? Beta. Or there's no reason why I couldn't have said a squared is equal to b squared plus c squared minus 2bc. Notice that these two correspond to those two. Cosine of side opposite a, which is alpha. So just make sure that when you set this up, whatever you call it, that this side and this angle are opposites or correspondingly, right? And same thing here, that this side and this angle are opposites each other. Okay, so let's solve a couple of examples. All right, so let's see. Here we go. Go thin. There it is. So it says solve for the triangle given A is 2, B is 3, and gamma is 60 degrees. So again, I like to just draw my triangle. Now, I know this is law of cosines because it's in the law of cosine section. But once we start getting both strategies together, the triangles will be mixed up. So it's definitely worth your while to draw a picture till you see, okay, what kind of triangle am I sitting in? Am I sitting in a side angle side or a side side side? Is it a dreaded ambiguous case like side side angle? Okay, so I have A as being 2. So I'm going to call this opposite angle at alpha. B is 3, so call this beta down here. And then this 60 degrees is gamma, which means this is C. So yeah, I'm sitting in, if you take a look, I'm sitting in a side, an included angle, and a side. So I'm okay. I'm in side angle side, no ambiguity. And I have a tool for that. I've got law of cosines. Okay, so law of cosines, I'll go back to my solving pen. So law of cosines says c squared is equal to a squared plus b squared. I'll just write it out this first time, minus 2ab cosine of angle c or gamma, the one that's opposite it. So then c squared equals 2 squared plus 3 squared minus 2 times 3 times 2 cosine of 60 degrees. Okay, so now I'm going to punch this in. And remember, you're solving for c squared, so don't forget to square root that. I see that happen a lot. So 2 squared plus 3 squared. And then minus 2 times 3 times 2 times cosine of 60 degrees, which actually is just 1/2. So we get c squared equals 7. That worked out nice only because cosine of 60 was so nice. So c would equal root 7. Most examples, you're not going to get such a nice, number. So if I actually get it to 3 decimals, we'd say it's about 2.646. Okay, so that's our value of C. Once we know that, 2.646, once you know that, now you can use either law of sines or cosines to solve for the missing angles. A lot of students like law of sines. Because it's an easier equation. Sometimes students will do law of cosines, that's fine too. But here's my word of caution. If you're going to use law of sines, which I'm actually going to, notice what is still missing, 2 angles. And so when you're going to solve for those 2 missing angles, that means you're going to need to introduce the sine function. And there's a potential of some ambiguity if you have an obtuse angle. There's only one triangle. So you have to pick the right one. And I always go through it in the chain of thought that there can at most be one obtuse angle. And the obtuse angle has to be opposite the largest side. So if there's potential for an obtuse angle, but I'm not sure if it's there or not, don't solve for that angle. So I know that I know one side length. If I look here, I know one side length is 2.646, one side length is 2, and one side length is 3. So if this triangle, if it were to have an obtuse angle, it'd have to be the one that's opposite the largest side, which is opposite 3. So don't solve for that one first. Don't find angle B or beta. Find the one that you're guaranteed to be acute. Okay, so I'm going to solve for this one, and I'm going to use law of sines, but I know that that's an acute angle. So when I introduce my inverse sine function, no ambiguity. I know it's just going to be whatever the calculator says. I don't have to worry about its supplement. So sine of alpha over 2 is equal to sine of 60 degrees over 2.646. So cross multiply. So 2 times sine of 60. And then I'm going to divide that by 2.646. And I'm going to do the inverse sine. And I know I'm introducing this. So I'm getting 40.889 rounded. Okay. Now, I know that that's the right angle. I don't have to consider like the supplement like we just looked at in the law of sines, because if you think about that, if you pick the 139, that makes no sense in terms of like that being an obtuse angle. How could that be the obtuse angle, yet it's still opposite the smallest side? So no ambiguity. I know there's just that one particular angle. And so once you know that angle and we know this side, the only missing piece is beta, and we can get beta by subtracting 180 minus the given 60 minus the 40.889. So 180 minus 60 minus 40.889, and we get 79.111. Excellent. Okay, so there's our 3 missing pieces. And again, I want to stress, when you're going back to find the 2 missing angles, when you have to go back, I guess, I don't know, purple, and solve for this angle and this angle. Pick the smaller one first when using law of sines, because then you know that this angle that comes out has to be acute because you've picked the smaller of the 2. Okay. All right, let's look at example 2. Here's a situation where I'm given 3 side lengths, 3, 4, and a 6. It says find each angle. And so, okay, so I'm going to find each angle. And again, drawing your triangle. Doesn't really matter how you draw it. So call this 3, call this 4, call this 6. Now, they didn't really give us a relationship with an A, B, C with the 3, 4, 6. So it doesn't really matter what you call it. Maybe call this alpha, beta, gamma. Okay. So again, law of sines is not going to work, so I'm going to need law of cosines. Now, there's a couple of ways, like there's a whole other like version of the law of cosines formula. But if you remember the version we had initially, we said, oh, it's c squared equals a squared plus b squared minus 2ab cosine of gamma, or cosine of c. And as long as the side here, and this angle here are opposite each other, then then your equation is fine. So I'm going to solve it one time, like just using this using this particular one right here. So let's say I'm looking for gamma. I want to find gamma. So that means what is opposite gamma is our 4. So then I would say, oh, okay. So go to this color. I would say 4 squared, because 4 is opposite gamma. Right? Those are opposites each other. So 4 squared equals 3 squared plus 6 squared minus 2 times 3 times 6. Again, this 3 and the 6 have to correspond to this 3 and the 6. Cosine of gamma, which we don't know. So now that becomes what I have to solve for. Now I'm looking for the angle gamma. So I'm going to treat that yellow highlighted piece as like a variable and isolate that. So we'll go back to my pen. So 4 squared is 16, 3 squared is 9, 6 squared is 36, and then 2 times 3 is 6, times 6 is 36. Cosine of gamma. Now this 36 is attached to this cosine of gamma. Initially, students might say, oh, I could do 36 minus 36. You can't, because that 36 is being multiplied by cosine. So I could do 9 plus 36 is 45 minus 36. cosine of gamma, subtract the 45. So now we have negative 29 is equal to negative 36 cosine of gamma, divide out that negative 36, and then do inverse cosine. So gamma is going to be the inverse cosine of whatever 29 over 36 is. So then I say, okay, inverse cosine of 29 divided by 36, and that means that gamma is equal to 36.336 degrees. Now, we introduced the cosine function, the inverse cosine function. So we need to be concerned, could there be another triangle that has that exact same cosine ratio of 29 to 36? One of them is in quadrant 1 that has a 29 to 36 ratio. The other one, if you remember, would be quadrant 4. In other words, it'd be an angle that's more than 270 degrees to get that into quadrant 4. That doesn't happen in a triangle. So that's the beauty of law of cosines, is that when you introduce cosine, you never have any ambiguity, because the only other positive angle that could happen would be in quadrant 4, which is way too big for a triangle. So now I know what my angle is. I know it's 36.336. So I know gamma is 36.336. Okay, so now I need two other angles. And if you remember what I said last time, when you're solving for these two other angles, you want to pick the smaller of the two, because law of sines, you could have an obtuse angle, and your calculator is only going to give you the acute value because it's programmed to give you the principal one. But if you're introducing that into the problem, you, being a smart mathematician, know that there's two possible answers. So between alpha and beta, I want to choose the acute one. And remember, the acute one's opposite the smallest side. Since 3 is the smallest side, I'm going to choose to solve for alpha. So I'm going to say sine of alpha, I'll go this color, sine of alpha over 3 is equal to sine of the angle I just found. And that's the hard thing about solving these triangles, is that you really need to check your work, because as soon as you solve an answer, that automatically is going to be needed almost always to solve the next thing over 4. So we cross multiply 3 times sine of 36.336 divide by 4. So we're getting a ratio of 0.44438, whatever. We're introducing the sine function, the inverse sine function. So we're getting alpha to be equal to 26.384. And again, if you remember, if this were in a law of sine setting where we didn't know if that was the smallest side or the smallest angle, we'd have to find its supplement, because an angle of 153.616 degrees has the same sine ratio. But we know it cannot possibly be that value, because that's an obtuse angle. And an obtuse angle can't be opposite the smallest side. So again, I know that this has to be the correct answer. And then if I know two of the angles, there's one angle, there's the other angle, I can subtract both of them from 180 to get what I'm calling beta. So 180 minus 36.336 minus 26.384, and you get 117.280 degrees. Okay, so now notice that is obtuse. And had I solved for beta, like first, I would not have gotten this answer. I would have gotten the wrong answer. Actually, I would have gotten its supplement. And that's the caution I'm going to throw, I guess, is that when you're solving for one of the two missing sides, law of sines, pick the smallest angle, because you know that it has to be acute. Okay, so I know there'll be some more examples. I'm going to go through with bearings and maybe even showing like what happens if you pick the wrong one, like where's the error, kind of an analysis problem. But I like that. That's a good start for law of cosines. Oh, the other thing I was going to say is that sometimes law of cosines is actually already solved for the angle, and so the alternate, I guess, equation for law of cosines sometimes is automatically already solved for cosine of gamma. And you don't have to necessarily memorize this, but some students do. 2AB. So as long as you associate this angle with what you're subtracting, then this is an alternate version that's automatically already solved for the cosine of gamma when you're sitting in a side case. Some students like to memorize that or use that. And again, you could interchange any of those particular letters. So I could have said, So I could have said, cosine of beta if I wanted to. Oh, I wanted a different color too. Let's go to green. I could have said cosine of beta. So then that would have meant a squared plus c squared minus b squared over 2ac. And again, just making sure that this b corresponds to this b, you'd be fine. Or you could have the other variation. Might as well put it here just to complete it all and appease my OCD. Oh, speaking of OCD, let's try this one more time. So we could say cosine of gamma beta alpha equals b squared plus c squared minus a squared over 2bc. And again, if you go to the highlighter and take a look at alpha and a, as long as those correspond, you'd be perfect. Okay, so that ends that video. I almost forgot to say that. You don't have to memorize those, but again, some textbooks present them, and so I just wanted just as a follow-up to that particular example.